Hello, I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at two extra things that you can customize when running a t-test. So, what we're going to do here is pick up with the example we did recently of an independent samples t-test, and we're going to look at how to first run this as a one-tailed test, assuming we had pre-registered that as our directional hypothesis. And then second, we're going to look at how to adjust the width of our confidence intervals. So for starters, I just went ahead and ran the code from earlier to run our basic default independent samples t-test. And you'll remember from earlier, the alternative hypothesis is just that there's some difference between the means. And sometimes that's what we want to run. Maybe we don't have a hypothesis. Maybe we have competing hypotheses. Maybe it's just early in the research and we don't want to commit to one side versus another. Maybe we didn't pre-register the study. So in any of those cases, a two-tailed test is fine. That'll control your error rate the way that you want. On the other hand, one-tailed tests can be more powerful. And so if you pre-register that ahead of time, and only if you pre-register it ahead of time, that can be a really great thing to do. Now, in principle, you could just run an ordinary t-test and then check that the direction is in the side that you predicted. So in this case, if you had gone in predicting that cat people would have higher estimates than dog people, we see here that that is the case. It's not significant, but it is in the direction that we predicted in this case. Well, if that's true, then running a one-tailed test is equivalent to having a p-value that is half of what you observe in a two-tailed test. Now, we all know how to divide by 2. So we could arrive at that answer easily enough. On the other hand, it's nice to have the code that we run reflect our actual intentions as researchers, which is why it's nice to see that the t-test function has an argument where we can specify whether it's one-tailed, and if so, what direction. So if we'd pre-registered this ahead of time, we could add this extra argument here that we didn't use earlier, where we set alternative equals greater. And that would be telling R that we are running a one-tailed test, and specifically that we expect the cat group to be greater than the dog group. And so earlier when we ran this as a two-tailed test, the p-value was 0.255. And now when we run it as a one-tailed test, the p-value is half as large. It's 0.127. Here, that wouldn't affect our conclusion, but it's easy to imagine cases where it would. Now, of course, just because you ran a one-tailed test doesn't mean the effect actually came out the way you expected. It could be leaning in the other direction. So here we might have expected the mean in the cat group to be greater than in the dog group. And if so, this is an appropriate way to analyze it. But let's just imagine for a moment we'd predicted the opposite, where the mean would be lower in the cat group compared to the dog group. Well, in that case, for alternative, instead of greater, we would specify less. And by the way, if you ever forget this, you'll recall from earlier that you can get more information about a function by putting a question mark in front of it and running that. And we have the options for alternative are two-sided, the default, or less, or greater. So we just saw what greater did. Now let's run and see what the p-value would be if we'd actually expected it to come out in the opposite direction. Well, in that case, the p-value is much, much greater, which makes sense because we're not even close to being correct about the direction of the effect in this case. So those are the options there. Again, I cannot emphasize enough, you got to pre-register this first, but assuming you pre-registered it, it is the closest thing to a free way to increase your power that I'm aware of. So that concludes running one-tailed tests. The other option that we can customize when we're getting really specific with the t-test function here is the confidence level. Now, just like the t-test defaults to a two-sided hypothesis test, reasonable enough, it also defaults to a 95% confidence interval. We're all aware of the customary p equals alpha level of 0.05 that we use as the cutoff for the false positive rate. Well, that corresponds to a confidence interval of 95%. So as a default, the t-test function, it assumes that that you are interested in the 95% confidence interval. So if we run the two-tailed version, we get a 95% confidence interval around the raw mean difference of being as low or as small as 4.39 skittles and as high as 16 skittles. But there might be cases where we would like to compute a 90% confidence interval if we're comfortable with a higher false positive rate. We can override the confidence level, and instead of leaving it at the default 0.95, we can enter this argument, conf.level, and here we could enter 90. And if we do that, everything's the same except for our confidence interval has become more narrow. Now it only spans from negative 2.6 up to positive 14. Now, it still includes 0, but it is more narrow, and the trade-off we pay for there is that we're going to be wrong more often. Now, we can also customize this in the opposite direction. We might really not want to be wrong, so we want 99% confidence, but of course we're going to pay for that in precision. In this case, the confidence interval is now much wider than it was originally. Now it could be as low as almost 8 and as high as almost 20. Now, because it's so wide, it will more often include the population mean difference on average. But of course, the reason it does that is because it's less informative. It's less specific because it's such a wide confidence interval. So the point for now is just that this is where that option lives if this is ever something that you need to specify. So that is how you do directional one-tailed hypothesis tests and how you update the confidence intervals for t-tests in R. See you next time.